High-frequency gravitational wave communications. 14 laboratory high-frequency gravitational wave, Hfgw, generators, or transmitters, have been proposed in the past 45 years in peer-reviewed journal articles. The most promising laboratory Hfgw generators are those that utilize very large numbers of sub-microscopic radiation elements. The piezoelectric approach to Hfgw generation is best for the proof-of-concept test, and the proposed IR-excited molecules approach is best for an operational communications Hfgw transmitter. 10 different Hfgw detectors, or receivers, have been proposed since 1978 and reported in peer-reviewed journal articles. Several different Hfgw receivers can be utilized for communication, but the proposed Lee-Baker detector, Plans and Specification Development in Appendix B, shows the most promise, underlying concept in Appendix C. The Lie effect, upon which the Lee-Baker detector is based, is not so new that it is untested in the literature. At least 9 peer-reviewed research publications concerning the theory have appeared following the initial peer-reviewed article by Li, Tang and Zhao, 1992. Because Hfgw communications are carried on an extremely narrow beam directly through the Earth, there is a very low probability of interception. Theoretical results confirm that the Lee-Baker detector is photon signal limited, not quantum noise limited, that is, the standard quantum limit is so low that a properly designed Lee-Baker detector can have sufficient sensitivity to observe Hfgws of amplitude AZ 10 to 32 m/m. Utilizing the IR-excited molecules Hfgw generator approach in the Lee-Baker detector, the theoretical information transfer rate over 7,000 km of distance, beamed directly through the Earth, is about 1.9 by 106 bits per second. A means of propagating a frequency time standard may be one viable early low bandwidth application for Hfgw communications. Hfgw sources on the Earth, the Moon, and Mars may act as reference standards for interplanetary navigation, with the advantage that they cannot be shielded or shadowed by planetary masses. Plasma interference seen at planetary entry would be eliminated, and precise charting of Lagrangian points would be possible. Introduction. Of the applications of high-frequency gravitational waves, Hfgws, communication appears to be the most important and most immediate. Gravitational waves have a very low cross-section for absorption by normal matter, so high-frequency waves could, in principle, carry significant information content with effectively no absorption, unlike electromagnetic, waves. Multi-channel Hfgw communications can be both point-to-point, for example, to deeply submerged submarines, and point-to-multipoint, like cell phones. Hfgws pass through all ordinary material things without attenuation and represent the ultimate wireless system. One could communicate directly through the Earth from Moscow in Russia to Caracas in Venezuela, without the need for fiber optic cables, microwave relays, or satellite transponders. Antennas, cables, and phone lines would be things of the past. A timing standard alone, provided by Hfgw stations around the globe, could result in a multi-billion-dollar savings in conventional telecom systems over 10 years, according to the recent analysis of Harper and Stevenson, 2007. The communication and navigation needs of future magnetohydrodynamic, MHD, aerospace vehicles, such as the MHD Aerodyne, www.prospects.com, which is high in electromagnetic interference, similar to plasma interference seen at reentry, would be another possible applications area for Hfgw communications. 1.2 Definition of high-frequency gravitational waves. Visualize the luffing of a sail as a sailboat comes about or tacks. The waves in the sail's fabric are similar in many ways to gravitational waves, GWs, but instead of sailcloth fabric, gravitational waves move through a fabric of space. Einstein called this fabric the spacetime continuum in his 1915 work known as General Relativity, GR. Although his theory is very sophisticated, the concept is relatively simple. This fabric is four-dimensional, it has the three usual dimensions of space, east-west, north-south, and up-down, plus the fourth dimension of time. Here is an example: we define a location on this fabric, Einstein, 1916, as 5th Street and 3rd Avenue on the 4th floor at 9 a.m. No one can see this fabric, just as no one can see wind, sound, or gravity. Nevertheless, those elements are real, and so is this fabric. If one could generate ripples in this spacetime fabric, many applications would become available. Much like radio waves can be used to transmit information through space, gravitational waves could be used to perform analogous functions. Gravitational waves are the subject of extensive current research, which so far has focused on low frequencies. High-frequency gravitational waves, as defined by physicists Douglas and Brzezinski, 1979, are gravitational waves having frequencies higher than 100 kHz. Low-frequency gravitational waves, Hfgws, such as those detectable by interferometric GW detectors, for example, the Laser Interferometer Gravitational Observatory, or LIGO, are not applicable to communications due to their very long wavelength, often thousands of kilometers in length and, even more importantly, the inability to generate them effectively in the laboratory. Furthermore, LFGW detectors cannot detect Hfgws. 2.0 Hfgw communications. Consider the case of a single point-to-point two-station full duplex communication system, as is represented in Figure 1. Such a system is often characterized as a single data link, and requires two transmitters, one at each end, and two receivers, one at each end. To avoid self-interference, the link in one direction often uses a frequency of radiation different than the link in the opposite direction. If one were to apply the emerging technology of gravitational wave control to such a link, one would use GW generators for the transmitters on each end, and GW sensors for the receivers at each end. Stevenson, 2009a. In the example shown in Figure 1, Station 1 would have a GW generator transmitting at a frequency of on and a GW sensor sensitive to a frequency of on, without being sensitive to a frequency of on. Likewise, Station 2 would have a GW generator transmitting at a frequency of on and a GW sensor sensitive to a frequency of on, without being sensitive to a frequency of 2. This is the minimum functionality required to constitute a communication link. Signal strengths of the respective GW generators would need to be sufficient to overcome link loss, coupling losses, and noises sources. Signal-to-noise considerations and link budgets are covered in further detail in Section 3.1. 2.1 Hfgw generators, transmitters. 2.1.1 Hfgw generator concepts. Several sources for Hfgws or means for their generation exist. The first generation means is the same for gravitational waves, GWs, of all frequencies and is based upon the quadrupole equation first arrived by Einstein in 1918. A formulation of the quadrupole that is easily related to the orbital motion of binary stars or black holes, rotating rods, laboratory Hfgw generation, and so forth is based upon the jerk or shake of mass, time rate of change of acceleration, and is derived by Baker, 2006, as where p is the power of the GWs, w, r is the distance between two masses, m, af is a change in force, n, over the time interval at, s, that is, the jerk or shake of the two masses, such as the change in centrifugal force vector with time, for example, as masses move around each other on a circular orbit. Figure 2 describes that situation. Please recognize, however, that AF need not be a gravitational force, see Einstein, 1918, Infeld quoted by Weber 1964, p. 97, Grishchuk 1974. Electromagnetic forces are more than 1035 larger than gravitational forces and should be employed in laboratory GW generation. As Weber, 1964, p. 97, points out, the non-gravitational forces play a decisive role in methods for detection and generation of gravitational waves. Equation 1 is also termed quadrupole formalism and holds in weak gravitational fields, well over 100 grams, for speeds of the generator components less than the speed of light and for or less than the GW wavelength. This last restriction may not really apply. Certainly there would be GW generated for or greater than the GW wavelength, but the quadrupole formalism might not apply exactly. For very small at, the GW wavelength, AGW equals cat, where C3 by 108 ms1, the speed of light, is very small and the GW frequency phi is high. As a numerical example, R is chosen to be 10 meters, convenient laboratory size, though usually greater than GW, AF equals 4x108n, for example, the force produced by a large number of piezoelectric resonators and at equals 2 by 10 3 degrees S, equivalent to about a Hfgw equals 5 GHz jerk or shake frequency, so that again equals 6 cm and P equals 2.8 by 10 53 watts or 0.28 picowatts. Clearly a very small Hfgw power is generated. One of the first suggested means for the laboratory generation of Hfgws was the so-called geyser analogous to the laser for light. Simply described, Halpern and Laurent, 1964, the geyser consists of a long rod of a material and microscopic parts of which can be excited by a means, such as electromagnetic, radiation, to emit Hfgws. They utilize linearized theory to treat the interaction of a gravitational field with matter. Application is made to the emission of gravitons by microscopic systems such as molecules and nuclei. Grischuk and Sazin in early 1974 discussed the emission of gravitational waves by an electromagnetic cavity. In August of 1974, Chaplin, Knuckles and Wood suggested the generation of Hfgws by nuclear explosions. In this same regard, Fontana suggested that the problem of efficient generation of Hfgws and pulses of gravitational radiation might find a reasonably simple solution by employing nuclear matter. Fontana and Baker, 2006, Fontana and Binder, 2009, especially isomers. A fissioning isomer not only rotates at extremely high frequency, 3.03 by 1024s, according to the aforementioned references, but is also highly deformed in the first stages of fission. The nucleus is rotating and made asymmetric before fission. Thus one achieves significant impulsive forces, for example, 3.67 by 108 N, acting over extremely short time spans, for example, 3.3 by 1022 S. Alternatively, a pulsed particle beam, which could include antimatter, could trigger nuclear reactions and build up a coherent GW as the particles move through a target mass. The usual difficulty with Hfgws generated by nuclear reactions is the small dimensions of their nuclear reaction volumes, that is, the small moment of inertia and submicroscopic radii of gyration, for example, 1048 meters, of the nuclear mass system. Such a difficulty is overcome by utilizing small clusters of nuclear material, whose nuclear reactions are in synchronization, for example, through the use of a computer-controlled logic system. Such nuclear-energized Hfgw generators are currently very theoretical. Brzezinski and Rudenko, 1978, discussed the generation of gravitational waves in the laboratory and proposed a means utilizing small particles. In 1981, Romero and Danon analyzed the generation of gravitational radiation in the laboratory, also utilizing a linear array of piezoelectric crystals that will be analyzed in more detail in section 2.1.3. In 1988, Pinto and Rodoli presented a paper on the laboratory generation of gravitational waves at the Italian Conference on General Relativity and Gravitational Physics. Another Italian, Giorgio Fontana, 1998, suggested that the possibility of emission of high-frequency gravitational radiation from junction between D-wave and S-wave superconductors. Krauss, 1991, proposed that gravitational wave communication might be possible in the IEEE Antennas and Propagation magazine. At the first Hfgw Working Group Conference at the MITRE Corporation in 2003, Grischuk analyzed electromagnetic generators and detectors of gravitational waves. At that same conference, Valentin Rudenko presented a paper on the optimization of parameters of a coupled generator receiver for a Hfgw Hertz experiment. At the second Hfgw Working Group Conference in Austin, Texas, in 2007, Kolisnin and Rudenko presented another paper on the generation and detection of the high-frequency gravitational radiation in a strong magnetic field. In 2007, and more recently this year, a new type of Hfgw generator/detector and mirror system based on thin-type superconducting films was proposed by Archiao, S. Minter, and K. Wechter M. C. Nelly, 2007, 2009a, b. Therefore it is evident that a number of devices for the laboratory generation of Hfgws have been proposed, including the aforementioned geyser, as has been mentioned, was first proposed by Halpern and Laurent in 1964, some 45 years ago, discussed by Fontana and Baker, 2003, as well as an actual laser generator of Hfgws as discussed by Lee and Lee, 2006. Finally, a rather practical laboratory Hfgw generator, which may be appropriate for the initial proof-of-concept test, is one utilizing off-the-shelf components such as magnetron-energized piezoelectric crystals or film bulk acoustic resonators or Hfgws has been analyzed in Woods and Baker, 2005, and Baker, Woods and Lee, 2006. The figure of merit for Hfgw generator is given explicitly by Baker, Woods and Lee, 2006. This figure of merit can be extended by considering other effects, since in the laboratory the force change could not even approach those of the celestial sources. It would seem that the magnitude of any laboratory-generated GWs could be best increased, 1. By utilizing electromagnetic forces rather than gravitational, 2. By increasing the distance between the gravitational radiators, 3. By increasing the GW frequency, that is, reducing at, and especially, 4. By developing a large number of in-phase system elements. This last effect enters as the square of the number of elements, n, as proved using general relativity analyses by Danon and Romero. Borges analyses, Romero and Danon, 1981, Danon and Romero, 2003. Such N2 dependence also may be the key to successful laboratory generation of GWs, especially Hfgws. In that regard, recent proposal by Woods and Baker, 2009, Black and Baker, 2009, proposed the use of infrared energized atomic nuclei, electrons and/or molecules, which have a very large N, contained in a stack of N waveguide rings, patents pending. The distance between GW radiators may be proportional to the GW wavelength in that it may have a limit that is less than or equal to a GW wavelength. The wavelength is inversely proportional to the GW frequency. Thus, given some value for the proportional constant, say unity or the distance between radiators equal to 1 GW wavelength, the GW frequency cancels out. As already noted, it is important to take advantage of square of the number of in-phase elements for useful laboratory Hfgw generation. If the elements are sliced in one dimension, the dimension along the axis of Hfgw generation, in order to increase the number of elements, then the change in force per element will be inversely proportional to the number of elements. For example, if the elements are sliced into 100 separate pieces, then each piece will have 1/100th of the force of the unsliced element. Essentially, F equals ma, and it is assumed that the acceleration of the element was the same after the split as before. This result also follows equation 8, page 17 in Baker, Stevenson and Lee, 2008b, and if there were 100 splits of an Hfg, then the power to an individual slice, P, and its mass, m, would be both 1/100th of their unsplit value, and the square root of their product would again be 1/100th. The frequency of the split elements may be a higher value, but the attendant increase in GW power proportional to the square of the higher frequency and the decrease in power due to a smaller distance between tracks, assuming that the distance between tracks is 1 GW wavelength, which would be smaller, would cancel, and there would be no net effect on Hfgw amplitude. It is concluded, therefore, that in this particular special situation the amplitude of the generated Hfgws is proportional to the number of in-phase elements, n, not the square. In any event, a large number of elements for a given Hfgw generator length can be best realized by reducing the size of the individual elements to sub-microscopic size, as discussed in U.S. Patent No. 6784591.